Great, thank you very much. So my name is Pontus. I'm a software engineer at Brockmann Consult in Hamburg. I've done a lot over the years in various combinations of geoscience and computers, and for the past 5 years I've been working mainly on the xcube ecosystem in the Python data stack, and in the last year increasingly on application packages. So what I'm going to be telling you about now is I'll give you an introduction to application packages, what they're good for, how they're structured. Briefly introduce xcube, at least the bits of it that we're going to be using, and introduce a new tool called xcengine, which turns Jupyter notebooks into application packages. So a quick pre-requirements check. Hopefully you found the course website and the list of preparation materials there. So hopefully you are sitting there with a terminal emulator, a Conda-based Python environment, and Git and Docker installed, and hopefully even the course GitHub repository cloned. If by any chance you're not prepared, I'm going to be giving slideshows and alternating between that and running through in a Jupyter notebook the active activities. It's possible to follow along non-actively, and all the materials will stay publicly available in the GitHub repo and on the website after the course. So anything that doesn't work or doesn't make sense or whatever, you can come back to afterwards. So as I briefly mentioned on the first slide, 3 main themes here: application packages. Officially, it's not a standard. We're not allowed to call it that. It's a set of best practices. The OGC are very keen on these distinctions, but it's a system that lets you package a huge variety of software into a standardized reusable module that lets you integrate it into cloud infrastructure workflows, and everyone's very keen on cloud workflows these days, so it's quite a hot topic. xcube, which you might have come across before, which is gets harder to define the more it expands. I think could best be called an ecosystem now for working with data cubes within the Python scientific stack. Today we're going to be concentrating on its server and viewer capabilities. And as I mentioned, xcengine, which bridges the gap between Python Jupyter notebooks and application packages. So just a little bit about how I'm going to present this. To my great regret, I can't be there in person, so apparently you can see me, I can't see you. But I'll be alternating between presenting chunks of slides. We have three sections, basically, one on application packages, one on xcengine, and one on xcube. And each one will start with some slides, and then we'll drop into the Jupyter notebook in the course repository and go through the practical bits. And at any convenient point, you can break in with questions if there are things that aren't making sense. I think probably most conveniently when we switch over from the slides to the hands-on bits. So on to the first part, application packages. First, the motivation. This is a term that I'm tripping over at least suddenly more and more the past year or two. I don't know if you've happened to encounter them in various projects, but the standard, or no, the best practice has been around for about 5 years, but suddenly they are becoming somehow integrated into a lot of projects and gaining more active interest. But essentially, it's a standardized way to put any EO processing software into a Docker image, and then add some extra information that lets it be executed on any standard platform. So it's a very useful tool for software reuse and reproducibility of results. So the 2 main components of an application package: first, a Docker image. So this is, for anyone who doesn't know what a Docker image is, very briefly a way to package up some software with a complete environment in which it can run. So a very general way to package and distribute software. This, however, in itself doesn't tell you exactly how to run the thing. You can give someone a Docker image and it might be very useful, but in and of itself, it doesn't tell you what to do with it, and they don't necessarily know how to run it. So there's a second component to an application package, and this is actually, it's best to think of this part as the actual definition of the application package, and the Docker image is usually where the interesting stuff happens, but this is really just a dependency of this CWL document. CWL is a common workflow language, so it's a mature, well-established language that lets you put together workflows, and it can have Docker image dependencies. And it basically tells you, or tells the platform that's running the application package, what inputs are allowed, what outputs are allowed. Basically, what do you actually do to run that Docker image that you've been given? Looking a bit further into this application package. So within the CWL file, in turn, there are two parts. There's the workflow definition. The workflow is the bit that you as the caller or as the platform that's running the application package is interested in. This basically gives the interface for anyone using the package from outside. Then the workflow definition attaches to a command line tool definition. Now the command line tool lives in your Docker image, so the command line tool is where the fiddly stuff happens to connect the outer interface to the inner interface to the Docker image. This is all sounding a bit vague at the moment, but we're going to get into details soon and see exactly how it works. So within the Docker image, you then have your actual processing code. This is whatever you wrote to do something useful before you started thinking about how to package and distribute it. Then there's some additional code to comply with the application package protocols, especially stack reading and writing is a big theme here. We'll come back to that. And then there's the entry point, which is the actual command line tool within the application package that gets called from the CWL file. What actually happens when this gets deployed? This is a part we won't be going very far into at all today, but just to put this in a wider context, your application package is sitting somewhere in a pod here on a Kubernetes cluster often, and this is running on a processing backend somewhere in the cloud. The common workflow language then interfaces this to the application package platform. And the application package platform on the other side interfaces to external APIs or pretty web portals. So the platform is really the thing that interfaces from the nice external interfaces to whatever's going on in your Docker image right at the back of the whole process. We are not going to set up a whole platform today to run application packages. Because that's quite a heavyweight operation, though there's a very brief bit about it at the end of this presentation. But there's a tool called CWL tool. This is a reference implementation for CWL, and this lets us locally run the CWL files. So this is not a full implementation of application packages, but it's a really handy tool for running and testing CWL and getting an idea of how it works. A little bit more for the wider context. This is what actually makes it useful. So this is something I borrowed out of an OGC document showing a wider Earth observation workflow. And this shows why you might want to put your code into an application package, because this is just then a standardized module that you can drop into a larger workflow, and it can be neatly reused without anyone needing to go into the command line level details of how to actually call things. Now let's dive into the actual details of CWL. This is what we're going to be working with when we go into the hands-on section in just a moment. So if the format looks quite familiar, this is because CWL is built on the YAML format, which is very popular everywhere these days. And it's got these two components that I showed in the block diagram a little bit earlier. So here's the, as it were, the outer part, the workflow. This is the part that will get called from CWL tool or from the platform that's running the application package. So we can go through this. It's got a few identifying things, label, documentation. You'll notice the input section is empty. This is a bit unusual, but this is a very simple example. Normally you'd have a list of inputs here because most processing workflows actually want some input data. And then correspondingly we have an output, and this, the format of this output actually comes from the application package best practice. You can see it's a directory. And this, in an application package context, means this directory contains any Earth observation data sets that I want to output. And we'll look in a little while at how the stack catalogs are written to actually define these outputs. Now, the next thing we need to know for the workflow is how to actually run it. And it has a bunch of steps which are run in sequence. Here we only have one step, and it runs something called MyScript. What's MyScript? We will come to that in a moment, but we look here first, we see out results. So it's picking up the results from MyScript and then passing them on to whoever called the workflow. Now we dive into the command line tool. This is what actually defines the processing code that gets called within the Docker image. You can see here's a Docker requirement. Docker image for Alpine, a very small Linux image. So this is a general purpose Docker image. Usually what you would expect in an application package is you build your own Docker image and put it in a registry somewhere, because you'll probably have so much interesting code there that it won't be convenient to encapsulate that all into the CWL file itself. You can see here, in order to keep things simple, CWL also offers the opportunity for you to take your Docker image and then write your own files into it within the CWL. So here we're just saying, write a file called myscript.sh, and then it just does that. It echoes hello world to a file. And here's a couple of details about exactly what gets called in the Docker image. And here's this output again. So you see outputs is results here. This is the same results that gets mapped to the steps up there. So there's a lot of boilerplate in a CWL. There's a lot of mapping things from one level and layer to another, and it's quite fiddly to write, but this is a problem we're going to solve later. You can also see here, this has an ID. This is very important. It's called MyScript. So this is the MyScript that got referred to in the workflow above, so that the workflow knows what to call here. Okay, after that introduction, we're going to switch into the actual Jupyter Notebook and do some hands-on work with CWL. If anyone has questions, this would be a good moment. If not, let's start it. Go on.
I think no. Is there any questions? Okay, no, we can go. Oh, no, yeah, there is one question. 1 second.
Just very simple question. How can we access the GitHub? I mean, the address. And to run this library, do we need some specific cloud computing platform, or we can run it on the laptop?
Everything we're doing today will be local. The address for the repository for this course was on the course website, which is linked in the pre-talks. So it's, here we are. xcube-dev/summerschool25. So if you haven't cloned that already, now's a good moment. But if you don't have it cloned already, you will need some time to set up the Mamba environment. So don't worry too much and just follow along. And as I said, this GitHub repository isn't going anywhere, and you can also try it out yourself afterwards if you just want to watch what's happening at this moment. So I forget if I answered the other question, whether it's only a cloud platform. As I said, we're going to be working locally today. In principle, the idea with application packages is that they be executed on the cloud. But as I'll mention briefly towards the end, it's also possible to set up a small testing environment on your local machine as a full application package platform. But this is something we won't go deeply into today. Were there any more questions?
No, I think we are good. You can continue.
Good. In that case, we'll dive into the notebook. So what I've already done here is, and hopefully if you followed the preparation instructions, this is what you did too, is to create the Conda environment with Mamba. So I'm now sitting here in the terminal with the Summer School 25 environment activated, which includes all the Python resources we'll need for this. I have to apologize. 5 minutes before the course started, I noticed that the README instructions have a mistake. It says you should execute Jupyter Labs Summer School 25. Actually, this is redundant. If you go into the directory and just execute Jupyter Lab on its own, this will bring it up. At least I sincerely hope so. So here we are. This is the contents of the repository. It's linked from the course page. I'll close that for the moment. And this summerschool.ipynb notebook is what will guide us through the practical parts. So the requirements is the same thing that I mentioned in the slides and that was on the course website. So we'll skip through that. Now, let's go to writing an application package. Here is more or less what I showed you before. So we don't need to go through this again. One thing I'll just show you that we didn't go through in the slides is that as well as writing the actual script here, we also write 2 more auxiliary files. A stack catalog, and the stack catalog refers to something called item.json, and then we have a stack item which refers to a file called hello.txt. If you've not come across stack, this is a now widespread standard for describing geospatial resources and increasingly all kinds of resources. And it's a fundamental building block of application package architecture. This is how the platform and the application package communicate about what EO datasets are going in and what EO datasets are coming out. In this case, the output is fixed anyway, so the catalog for the output can also be fixed. In general, though, if you're implementing something as an application package, you need to write custom stack entries for whatever happens to be getting output. So hello text here is simply the file that's being written here. This is, of course, not really an EO data file, but Stack doesn't care about that. It's happy to present that as an asset as if it were EO data. Now, having looked at that, how are we going to run it? Fortunately, as part of this environment that we installed with Mamba, CWL tool, which, as I mentioned, is a reference tool for running common workflow language. It's provided as a command line tool. Just look before we run it at what the parameters are out there, the output directory, where it's going to pull out any files that the CWL produces. And here's the reference to the file. And here's the identifier of the workflow. If we go in here, we see that the workflow is in fact called hello. And that's how it knows what to find in the file. So off we go. It's found the workflow. It's run it in Docker, as you can see. And this is why we're using a very minimal Linux Docker image, because this is very fast to download, even if there are many of you sitting in a conference room all using the network at the same time. And then it runs myscript.sh, and then we get a little overview of what was in the output when it finished running. And you can see the hello text file, the item, the script itself, and the catalog. And it successfully ran, which is nice. So where did we tell that to put the output? In hello1. CWL tool always puts this randomly named subdirectory in for reasons we won't go into. So we dive into there, and now we can actually look at what came out here. Here's the catalog, and that links to the item, and the item links to the hello.txt, and the hello.txt says hello world. So far, so fascinating. So you might have thought this is quite a lot of overhead for a very simple process. Yes, of course it is. Proportionally for a large processing workflow, of course, the additional effort for this stuff is a smaller proportion of the whole project, but this is all leading up to XCEngine, which will make the whole thing easier. Before we make it easier, we're going to try making it harder, which is to say we're going to actually implement an input. I mentioned that inputs is empty in this example file, but we can change that. So let's just look at what's required to implement an input. First, we go to the workflow part, and we find the bit where we had this empty input, and we paste this in. Oops. And that's the outputs. There we are. So we're just saying that we have an input called name. It has a type of string, and the default value is world. But this is not enough yet, because the workflow doesn't know what to do with this input. So how do we carry on here? Well, first, we need to go to the run script section and tell it that the name that the workflow gets, oops, I shouldn't do that, that the name that the workflow gets is the same as the name that you pass into the step. So this goes in here. And then as the next part, the command line tool needs to know what to do with this name that it gets. And we're telling it input binding position 1, which means you supply this as the first argument. And this goes in the input section of the command line tool, which I think was way down here. There we are. As you can see, as always with YAML, it's always fiddly with the indentation. Yes. Yes.
Yeah, unfortunately, we lost you for a minute, I think, because of internet connection. Maybe you can can you please let me to choose another network for a sec?
Okay. Okay.
What's your name? Refresh. Yes, I think we are back. Would you
Okay.
please repeat the last minute?
The last minute. Okay, I'm not
Where-
sure exactly where I was 1 minute ago, but basically we were going through the. I'm getting a really bad echo here. Is there a microphone you could deactivate somewhere? Testing, testing. Ah, that sounds much better.
It is better? Okay.
Okay, it's still a bit of interference, but we'll try to get through it. I think it'll be fine. Okay, so I'm not sure exactly where you lost me, but we were working through this cell in the notebook here. So if you're following along with the notebook yourself, then fortunately you don't need to catch everything I said. You can just follow the instructions in this cell, which I was also going through in real time. And I just got to the final one. The theme here is we have 4 different places where we have to link up this parameter to where it actually gets used. And we've just reached the last one, which is the script itself. And now we replace the world here with $1, which in shell script means whatever the first parameter was. So let's see if I got all those indentations right and run it again. And you can see this time, this is what CWL tool helpfully lets us do. Is it takes any arguments here and passes them on to the workflow. So this newly defined name argument gets implemented as -- name on the command line. I'm actually mildly surprised that I didn't make any typos there. Okay, so here we are. It wrote its output to hello2. Final status is success. And let's take a look at that output. We don't need to dig through all the stack entries this time. Let's look at this. And sure enough, it's now hello Jeff. Good. So I mainly did that to show how fiddly it is to write CWL by hand. And now we'll go back to the slideshow and I will present something to make this a little bit easier. Oops. Let's go with that. Now we'll start looking at Jupyter Notebooks a little bit, because a lot of us use Jupyter Notebooks as our everyday development environment, and a nice sandbox and a good way to easily interactively put together processing code. What would it take to turn a Jupyter Notebook into an application package, and how easy could we make that? Well, fundamentally, they have quite a lot of differences, even though they're in some way both about running processing software. So let's take a look at where these differences are. Python environment, Jupyter Notebook itself doesn't care about that. You generally have to do what we did setting up today, which is create and switch on your environment and then start the Jupyter notebook in that environment or configure a kernel with a pre-created environment. The application package doesn't care about environments, but doesn't care in another way, which is, say, in an application package, you put together or specify your own Docker image, and then it's your own responsibility to set up the environment there. So with application package, the environment always has to be included somehow. The parameters. So as we just saw for an application package, implementing an input parameter requires a lot of strict definitions with types and defaults and linking it up in the CWL file. By the way, they don't add all these layers of boilerplate just to be difficult. This makes CWL a very powerful and flexible format. But if all you're doing is trying to link up a parameter name at the workflow level with a parameter name within your code, then it feels like a lot to go through every time. Jupyter Notebook doesn't really have a concept of input parameters, so there's a few external utilities that have implemented something like that. So if effectively you can make any variable a parameter, you just highlight it in a documentation cell and say, hey, if you're using this notebook, you can change this value. And there's not really a formal definition in the same way as an application package. Data input output, which I've marked here with a warning sign because this is really a biggie. Jupyter Notebooks, much as with parameters, they can read or write data however or whenever they like. Application packages, sort of on a technical level, they can do that, but as we saw in the first part of the concept of application packages is plumbing them into a workflow. So ultimately, if you want to get the maximum use out of this, and if you actually want to write an application package that can be reused in a variety of processing pipelines, you need to conform to this stage out and stage out with writing these stack catalogs and also reading stack catalogs for input, which we're not going to look at very much today, but it works the same as what we saw, just the other way around. So distributing a Jupyter notebook, you just need to distribute the notebook itself and an environment file of some kind. And distributing an application package, fundamentally all you need is a CWL file. And the Docker image is usually a dependency, but if you put your Docker image in an accessible Docker registry somewhere online, then you can deploy a CWL by just giving the platform, you can deploy an application package just by giving the platform this CWL file. So what it comes down to is fundamentally a Jupyter notebook is an interactive environment that got so popular and useful that people now want to use it for things it wasn't originally conceived for, like non-interactive workflows. The application package is strictly fundamentally batch. There's really no way to interact with an application package while it's running. You give it its inputs and you wait for it to run. So what would you need to do if you want to turn your notebook into an application package? Well, first you need to make a runnable script out of your notebook, and you can already use command line utilities to run a notebook all the way through. And there are third-party utilities to help with this as well. Papermill, notably, if I remember rightly. And because you're going to be running in a Docker image, you need to process command line arguments. This is not something you get for free in Jupyter Notebook. So you need to pick one of the 50 Python command line processing libraries and implement something for that maps your command line arguments onto variables in your notebook. And then you need to read the input data via stack catalog, provided that assuming that you actually want to conform to this pipeline workflow pattern. And then you need to write your output data and write a stack catalog for that. Once you've got that, that's your that's the code support completed, but you still need to define a container image. You need to pack the code into a container image and publish that in a public registry somewhere. And then you need to write the CWL file with all that boilerplate linking up your command line parameters to the workflow parameters on the outside. And because we're not perfect, that will probably involve a few debugging cycles until it all works. So the question is, how much of that boring stuff can we automate? The answer, it turned out, was a surprisingly large amount. So here we have XCE tool. It's the name of the utility I started working on last year, which tries to perform this feat as conveniently as possible. So just for clarification, this was perhaps an unfortunate naming choice. The package is called XCEngine, but the actual command line tool that we'll be using today is called XCE tool with a small x. PowerPoint doesn't like small x's. So this simply takes the notebook and the Python environment. Even the environment is optional, but strongly advised, and does some magic, and then it spits out a Docker image, which can be used in an application package, and an accompanying CWL file, and which handles most of the fiddly stuff. In general, you don't need to touch the CWL by hand. There's also a part 2 here, which is a built-in xcube server and viewer in the Docker image. That's got nothing to do with application packages, but it's a nice bonus feature, and we'll come back to it later. So what exactly is XCEngine doing here? Parameters. So I mentioned Papermill. This is another tool that helps to run Jupyter notebooks as scripts. And Papermill introduced this concept of a parameters cell, and since this is then a sort of mini de facto standard, XCEngine also uses this. You just need to tag one of your notebook cells, and then anything in that cell is a parameter. We'll see in detail how that works in a moment. And once XCEngine has identified a parameter, everything else can be automated. So it can can provide command line argument processing, the type definitions for CWL default values, which are taken from the parameter cell itself, and all the fiddly CWL bits that link different levels to each other. For the data stage out, this is surprisingly easy for XCEngine to do. At the moment, we only support X-array datasets for stage out, but it's easy to add support for more. So XCEngine just goes through the current namespace after the notebook is finished running, finds any datasets that are lying around and accessible and assigned to variables, and writes them out and automatically produces stack catalog entries for them. The environment, it's expected that you supply an environment. You need to define an environment for your notebook anyway, so usually you'll have an environment.yaml file lying around. XCEngine can also try to determine the current environment, but it's really something that's impossible to do completely reliably, so it's a bit of a last resort. Anyway, once you've fed all that in, what comes out is a Docker container image and a CWL file. So, quick preview of the notebook that we're going to be playing with here. This is a notebook that creates some synthetic data, so it doesn't need to interface to any external data stores. This is to keep things a bit more simple and reliable for live demos. And this notebook's included in the course GitHub repository, so we can start looking at that in just a moment. An important note before we get to it in the notebook itself. So this is the parameters cell that I was talking about. And this is the practice that we've borrowed from Papermill. So at Jupyter Lab, as if you click up here to the top right, there are some extra tools in the notebook, including a property inspector. And this means that on any cell, you can tag it with any any tags that you want with any names you come up with. So parameters doesn't have any special meaning to Jupyter Lab itself, but parameters has a special meaning to xcetool when you run the conversion. And xcetool then knows that within this cell, any variables you define are going to be taken up as parameters. And as you can see already from this, xcetool knows the parameter's name, the default value, and it can infer the type there, and that's enough for writing the CWL file. You see also there's another sort of magic definition here, xcengine config. So we can actually integrate some of the configuration for the xcengine into the notebook itself, which is usually the most convenient place to have it. We'll go into that further as soon as we go hands-on. Okay, so now we can switch to the hands-on bit, and if anyone has any questions, then now would be a good moment.
Yes, any questions? I don't think we have any questions, Pontus.
Good. Which means I was either completely clear or completely confusing.
I will go with completely clear.
Thank you. Well, hopefully it will be even more clear after the hands-on. So here we're going to look at this notebook that we just saw a screenshot of. Let's just, actually, we're going to reverse these stages because doing the conversion, especially building the Docker image, is going to take a little bit of time. So if you're set up here, what you can do is scroll down a little bit past here. And I'll just briefly analyze this command line here. So xcetool, as I mentioned, is the name of the command line tool for xcengine. And like many modern command line tools, it has a sort of hierarchical command structure. So image is anything to do with the subcommand for manipulating Docker images, and build is the sub command to build one. EOAP stands for Earth Observation Application Package. So if you add this option, it means also make an application package and write the CWL definition to this file. And then final argument is just the notebook we want to input. So I'll start running that now. For me, because I have some cached Docker data, this will probably go quite quickly. If you don't have a cache warm and ready, then it will take a few minutes. So that's some good time that we can use to talk through the input notebook itself. Now, looking at this, we have this notebook, which we'll open in a moment, and an accompanying environment file. As I said, it's best to supply the environment explicitly to xcengine, to xcetool. Now, the Docker image that's going to be built here will only be available locally. Obviously, if you're deploying to a cloud platform, then you'd want to push it to a public registry. But if we're only doing local tests with CWL tool, then it's fine to keep the image local as well. And obviously that avoids the problem of a large number of people all simultaneously pushing multi-gigabytes through the conference Wi-Fi. So now let's actually go into this notebook and see what it does. So this notebook just works with some very simple synthetic data. It doesn't have any scientific significance. It's purely fake data to demonstrate how everything works. Here is our first actual encounter with xcube. Oops, I'll keep doing that. We're just going to use xcube here to generate this synthetic data. But really, we could use any data here and generate it any way we like. So here's an introduction to the parameters cell that I just gave in the slideshow a moment ago. And here's the one actual parameter we have, periods, which defines how many time periods it's going to have. So whatever value gets set here gets defined in the application package as the default value, and that can then be overridden by providing an argument to whatever's running the application package. Now, we can go a bit further into this xcengine config. So this is like the I'll just show how to get into the tags here. So property inspector is up here. And if you go into the common tools, you can see this parameters tag here is here. As I said, you can add any tags you want there, but this is the important one if you actually want to define that. The other magic thing you can have in a parameters cell is this special name xcengine_config. It's not necessary. Xcengine can use default values, or it can take arguments on the command line, but obviously it's quite convenient to configure your conversion within the notebook itself. So here we supply an ID for the workflow. We tell it where to find the environment file, so it doesn't try to do that for itself. And we give it a name to tag the image for. And this is where, if you were on a public registry, this would be a tag referring to something on Docker or Key.io or GitHub or some other public image registry where you could actually push it after building it. Now, looking at the data sets, we won't go too deep into how these are created. Xcube core new here. So this is simply a useful utility library within Xcube, which helps you to generate example data. And this just works by defining some variables. And here we're defining a variable from a lambda function in Python, which is to say, this is an inline function that just takes the position and the timestamp and performs some very basic modular arithmetic to make a pretty pattern depending on the current time and current location. The nice thing about this is it's actually generated on the fly. So this is a nice demo of the lazy or on-demand processing facilities that we get in the in Xcube and in the Python's scientific stack in general. So for running the application package, it's not interactive. This all has to be generated anyway, but we'll see later when we get to the viewer that this on-the-fly generation is actually quite a nice thing to have. So we create another data set, just to have something more to play with. And then we can just try out plotting one of them within the notebook. So here we select the first time step, select the only variable. And as you can see, that very simple equation there has produced a rather dramatic stripy pattern, which if you look at the latitude and longitude, you can see covers the entire Earth and has the mysterious name of V. Of course, for the actual application package, we didn't need to do that. This is just a neat check to see that the notebook itself is doing what we expect it to. And actually, we don't need to do any more than that. This is enough for xctool to get on with, because what we have here is two cubes. Xcube core new cube generates, we can see what it is. Oh, I haven't actually run it, so we can't. But if we actually run those, we can see that cube 1 is an X-array dataset. xcengine will pick that up from the data type and pull that out automatically as an output dataset and handle everything connected with that. So hopefully for anyone who's following along, this will also have completed now. It takes about 3 minutes on my computer. And here we get the confirmation that we've got an image built with the tag dynamic:1. Now, how do we run this? So, just the same as we did it before, we can use CWL tool, tell it where to put the output, in which directory, tell it what the CWL file is, tell it what the name of the workflow was, Remember, this is the same dynamic that we set here in the configuration. And if we want a non-default setting, we can add an extra argument there. So off we go. Here we can see it running. Oh, because instead of the 30 megabyte Alpine Linux image, this is using the 2 gigabyte Python scientific image that we just built. This takes a little bit longer, but you can see it's finished. And again, it tells us what came out of it. And what came out was actually quite a lot, because XCEngine writes ZAR files, and CWL tool helpfully lists every single file that was output, and the ZAR archive consists of many small chunks. So we get a huge list here of every single chunk in this ZAR file, which is very helpful. The CWL tool, but I'm just going to clear this output so we don't end up with a 800-kilometer long notebook here. Now, as we see, we have this dynamic output file, and just as before, we have something in there. So what we're going to do to look at the results now, we won't just dive in by hand. We'll pretend that we are an application package platform running this code and see how the stack catalog works. Now, this was the stack catalog that's automatically generated by XCEngine when it does the processing. So we're going to use the standard Python PyStack library to navigate through this stack catalog and see what happens. So first we find the path to the catalog. We don't know in advance what this random directory name is going to be, so we glob that. Okay. It's always one bug. If you're following along, please import glob before trying to do that. Now we go through here, open up the catalog, look for the links to the items in the catalog, and we can see we already have links to both these JSON files, which are further stack entries, this time stack items. Now let's find the path to the first of those items. So we've resolved this now relative to the catalog, and this is the full path to the item. Now we can look at the item itself. So what's in here? What has XCEngine done for us? Well, we have a geometry in the approved format, as we can see, 0 to 90, 360. It's covering the whole world, as we saw already in the plot within the notebook. Bbox has the same. It has the start and the end time also taken from the default values in the generated data. And most importantly, apart from these boilerplate links here, we have the assets, and we can see there's one asset listed here, and it's a ZAR, and we have a path to this asset. So we can go once again, carry out the same process, use PyStack to read that out. Oh, another library I forgot to import. So import pathlib here, if you're following along, and we have the final path. And from that, we can open a data cube. What does this look like? Well, it's got a time dimension of 20, which is what we would have hoped for, because you remember we specified periods 20 there, so it's overridden the default of 10, and we have 20 time slices. What else? It's got the default data variable v, and just to confirm that it's the data that we were expecting, we can once again plot it, and we have that eye-searing stripe pattern once again. Now, just as we did with the built-in with the handwritten CWL, we're going to try adding another parameter. But in this case, it's going to be a lot easier. So what are we going to do? Let's start by copying this. Duplicate notebook. And then in here within XCengine NB, we should have this. Let's rename it something like Dynamic 2. And then let's do some changes on this. And what we're going to do is add a new parameter. So we'll add a parameter for the name of the variable for one of the data cubes. So we'll call it var name. Is that what I'm calling it in the documentation? I think so, yes. So we add here, var name is foobar. So this is already defined as a parameter. That's actually enough for XCengine, but we actually want to do something with it, of course. So let's just use it in which cube did I want to use it in? Cube 1, exactly. So instead of variable v, we'll have variable var name here. And we'll just change this tag to dynamic 2. So this way we won't overwrite the image that we just created, but we'll create a new one that we can run separately. Now let's take a look at this. All we need to do, hopefully, is run this again. So this time we output dynamic 2 and we input dynamic 2. And the build, even for anyone who had a slow build last time, should have a fast one this time, because Docker is very good at caching, and it's just this tiny change we need to put on top. So now we can once again run this. So this time we run dynamic 2 CWL, pick a different value for periods, and now let's try supplying a value for our newly defined parameter, and let's call it Jeff instead of foobar. And off it goes again. And once again, we get the entire contents of the ZAR files lovingly listed for us, which we can clear from this cell. Now, just do the same thing as we did before, navigating through the stack. And at the end, we pull out a data set called DS2. What does DS2 look like? Well, we can see it has 12 time slices, and it has a data variable called Jeff instead of V, or instead of foobar, which was the default variable, default value. So we can see that all got picked up, and with basically one line of code, we added another parameter to that. So this is what XCengine can do for you compared to putting together your CWL by hand. And now we will go back to the slides for a bit and look at the extra bonus functionality that's built in here. Now, in the overview of what XCengine produces earlier, there was a little reference to xcube. So I'll do the one slide introduction to xcube, because I don't know how familiar it is to how many of you. There will not be a test on this. This is the 10,000 foot overview, and this is just a little bit of context to show what xcube includes generally. So the bits that are going to be relevant for us today, I will say, first up are the viewer and the server here in the middle. But we'll start at the top left here, because this is somehow the core of xcube. It's a library, or I don't know, a set of libraries, an ecosystem that sits on top of the pre-existing Python data science stack. It builds heavily on Xarray, and it has it has a lot of functionality for manipulating data cubes. We saw a brief usage here in the example notebook where we used it to put together a synthetic cube, but it can do all kinds of regridding and manipulation and generation. But what it also includes, and what we'll be concentrating on here, is the xcube server. So this is an API server that has a pluggable API architecture, supports a large number of in-house and standardized APIs. We'll see it running in a short while. And amongst other useful things, it actually has an S3 object storage emulation. So you can have a dynamically generated, computed on-the-fly processed data cube sitting in xcube, served through the server. And the data is only produced on demand, but it's served up, for instance, through an S3 that just looks like a standard Amazon S3 AWS storage bucket. And the most photogenic component of the server is the built-in web viewer. So the web viewer is a JavaScript client-side web application that opens in your browser, and it uses one of the xcube server APIs as a backend. So the xcube server is providing the data sets, and the web viewer is providing quite an extensive friendly user interface to them. Just sitting at the bottom here are xcube data stores, which we aren't going to talk about at all really more today, but this is just so you know that xcube's another core piece of xcube functionality is this modular data store architecture, which means that it's easy to implement a new data source, and I don't know how many we have, 12, 20 so far, which interface to all kinds of external data stores and third-party services and protocols, CCI, various Copernicus data stores, various ESA data stores, various file formats and online protocols. And then there's also a vector feature database called GeoDB, which ties in, but we won't go any further into that at all. Time's getting a little short. So the xcube server and viewer, what we'll be concentrating on now. Here's a slightly more close-up view of the viewer. The server is distinctly less photogenic, but you can at least open up the API endpoints in your browser and see that it's serving up data there. Now, the clever thing about the Docker image that XCEngine outputs, you remember I said that the CWL is necessary to tell us how to run the Docker, because in a Docker, there's no single, I mean, it's just a package of software, so there's no single compulsory way to run the contents of the Docker. You can change the arguments, you can change the executable, you can do whatever you like with the stuff that's packed in there. So what XCEngine does is to pack some extra functionality in there. As far as the CWL file is concerned, this is just a batch runnable Docker image that implements application package functionality, but it also supports a -- server parameter when you run it. And if you pass that into the executable in the Docker image, then you get an entirely different feature set, which is to say you get precisely this xcube server and viewer constellation that I mentioned on the last slide. So without further ado, we're going to dive in and actually just do that. But if you have questions, you could ask them now. That sounded like no questions.
No, we do actually have questions.
Oh, carry on.
Hi, thanks. I was wondering, the tool writes out all the cubes which are in the notebook. So if you have a process that then defines some intermediate cubes, those are also written out, right, by the
Yeah,
tool?
exactly. So if you have an intermediate cube, then you need to, Python has this convenient del command, which means delete something from the current namespace. So if you have intermediate cubes that you don't want to be written out, then you can just hang on a final cell on the notebook where you do del intermediate cube or whatever it's called. And then the variables are no longer in scope and XC Engine won't pick them up when it's doing the conversion.
Okay, thanks.
Any other question? No, I think we are good. We can continue.
Great, thanks. Now, so to do this, it's pretty simple. As I mentioned, it's actually done with a parameter to the executable that's inside the Docker. But it can get a little fiddly because we're mapping the port where things are being served. So for convenience, xctool also offers this image run subcommand. And we demonstrate here the port argument to this. The default port is 8080. But I frequently try to avoid this one because it's quite a popular port name, and then you can get a clash if you happen to have something else running in the background on that. But in any case, we can just run this as it is. Actually, I've never tried running it from a notebook before. But why wouldn't it work? And it says it's waiting for the container to complete. But of course, since the container is running as a server, it's not going to complete. It's going to sit there serving until we turn it off. So now we can click this link here, the port that it asked for. Somewhere on my desktop, it has now opened the server. So as I mentioned, yes, for human use, a server is not very exciting, but we can at least look through and admire all the APIs that are supported here. For a slightly more human-friendly view, it also supports OpenAPI. So this is a very convenient way if you are digging into xcube and wondering if it supports an API that you're interested in or how one of those APIs works. This is the viewer API, so this is the backend for the viewer that we're about to see. And we can see it's a standard OpenAPI presentation where we can dive into any of these. So if we go in here, we start seeing some of the more standard APIs, OGC API coverages, which was implemented 2 years ago, I think. And these are just modules supporting any API you like. So this makes xcube a really useful clearinghouse between different data formats and sources, because at the back end, we can plug in these flexible data stores that I mentioned to all kinds of backends and formats. And then at the other end, we can feed things out through these various APIs that are supported. You can actually even daisy chain multiple xcube servers talking to each other, but this is more entertaining than useful for the most part. So looking at the xcube viewer then. And here we see this now rather familiar, painfully stripy dataset. This does not tell us very much at the moment, and in fact it won't, but what we can at least do is click on the color bar here and reduce the opacity. So that will at least convince us that this stuff is some kind of geographical data. And we can now see the base map shining through. And of course, here we can also fiddle around with all kinds of pretty color schemes and different scales. And naturally, it supports everything you'd expect from a viewer like this, zoom and pan. And you remember we had 20 time slices in here. So we can also select time. We can step through time, and we can animate. And as I mentioned, this is all dynamically generated. So you saw the equation that's being run in that notebook. It's just being called whenever a pixel needs to be calculated, and then for a bit of extra speed, the viewer application caches it client side after it's been shown the first time. So you can see it judders a little bit the first time it's updating, but then eventually it gets cached. And then we don't really have time, and it's not the main topic here, to do a full run through of the viewer features, but just to show some of the more fun stuff, you can, for example, draw polygons on your map and then look at evolution through time of those polygons. Oh, yes, well, averaged out, anything that big is going to be quite boring. Let's try it with a smaller polygon. Here we can see that the time series follows the marching stripes going across the landscape. And really there's more than I really have time to go into here. So we can also add point locations, which get the same kind of thing. We can look at statistics. We can actually even define our own statistics. We can define user variables. I invite you to dive into it at your leisure if you want a fun toy to play with. You can also export the data. It's a continually growing, very versatile data viewer. I think that's probably about all we need to look at here. Do I have anything more planned in this? No. So I think at this point, either I could move on to, where am I here? I could move on to the optional section about application package platforms, or if there are questions, we could use these last minutes for some questions and answers.